Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. It's been a while since we put out an academic video, so I wanted to continue our Algebra 2 series on logarithmic functions with this video where we're going to be covering common logs along with graphing, and then we'll do an introduction to translating logarithmic functions graphs. So again, in this lesson, we're going to be understanding what common logs are. We touched base on them in the last video with a word problem, and I kind of went over them, but I did want to include at least one slide of information and then two quick problems, just so you understand what common logs really are. And then we're going to do an introduction to graphing, and like I said, after we do the introduction to graphing and then do one quick graphing problem together, then we'll be talking about how we're going to translate log functions as we've translated linear functions, quadratic functions, and every other kind of function that we see. You can do the same thing with log functions, and I'll show you how. Before I get into this video, I would really appreciate it if you could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. It's all very much appreciated. So let's jump right into the lesson. Let's first talk about common logarithms, like I promised. Simply, a common logarithm is also called a decadic logarithm, I think that's how you pronounce it, and a decimal logarithm. You might also hear it by those names. It's basically just a logarithm with base 10. So as we saw, usually our bases change, and they can range from any integer value above 1. But when we have a base that's a 10, so if we have like log base 10 of some number, we don't actually have to write the base 10. So you can see when you write a common logarithm, which is log base 10 of some number x, you can simply write it as log of x. You don't need to include that tiny subscript 10, which indicates the base of the log, because a common logarithms already assume that you're in base 10. So you don't need to show the 10. That's pretty much what a common logarithm is. So whenever you're working with logs, you might see situations where you have log of x, some variable representing some number, and you might not see a base. When you don't see a base specifically indicated to you, a base as in a subscript, that means you can automatically assume you're working with a common logarithm, so the base is going to be 10. So let's do two quick problems just so we're familiar with what base 10 looks like. So first problem is we're trying to find the common log or log base 10 of 100, and I know this because there is no base actually written in this problem. There's no clear base indicated, so we automatically assume it's 10. So in this case, what we're going to do is we're going to set log base 10, which is of 100, so log of 100 equal to x. So we're pretty much trying to find out what x is. Then what we're going to do is we're automatically going to assume that the base is 10, so we're going to use an exponential function, rewrite as an exponential function, raise that base 10 to the power of x, and set that equal to 100. So we're pretty much trying to find out how many times are we multiplying 10 by itself to get 100, and that's the solution to this. So we're pretty much raising 10 to the power of x equal to 100. Then we can rewrite 100 with the same base as 10. So 100 is 10 squared. So 10 times 10 is equal to 100. 100 is a perfect square. So we can rewrite it as 10 to the power of x is equal to 10 squared. Since the bases are equal to each other, the exponents are equal to each other. The exponents are x and 2, so x is equal to 2, and that's how we solve the first common log. Here's the second common log. We're trying to find the common log or log base 10 of the fraction 1/10. So in this case, what we're going to do is we're going to set that equal to x. Again, log base 10 of 1 over 10 is equal to x. Then we are going to take that base 10 and then rewrite it as 10 to the power of x is equal to 1/10, which is the fraction. So we're trying to find how many times do we multiply 10 by itself, or what number do we need to raise 10 to in order to get 1/10. In this case, what's going to happen is when we raise 10 to the power of x, we're trying to rewrite 1 over 10 in terms of 10 as a base. Whenever, as you can see, this is a fraction where 10 is the denominator. When 10 is in the denominator, you automatically know that the exponent is going to be negative. So in this case, we have a negative exponent, and then it's just going to be a negative 1, because we're raising 10 to the power of 1, which is equal to 10. If we're working with a fraction, for example, 1 over 100, 100 is 10 squared. So if we rewrote 1 over 100 with a base and an exponent, we'd have 10 to the power of 2, but it would be 10 to the power of negative 2, because 100 is in the denominator since we're working with fractions. So in this case, is 1 over 10 is equal to 10 to the power of negative 1. Since the bases are equal, the exponents are also equal, so x is equal to negative 1. So that's how we work with common logs. Pretty simple, quick just overview of what that was. So now let's get into graphing. So we're going to look at the graph of a log. A logarithmic function is the inverse of an exponential function. So remember, an inverse is pretty much the reverse or the opposite. So if you have an exponential function, a log is the reverse or opposite of it. So if you have an exponential function, if you put an input x, you get an output y. By the laws of inverses, if you take that same input and output, if you actually input y, you're going to output x with a log. So that's what inverses are. It pretty much undoes what the other function did. That's the summary of what inverses are. I'm going to show you a graph, but the graph has both the graph of the exponential function y equals 10 to the power of x and its inverse y equals log x. I'll be showing you that. Keep in mind that the y equals log x is a common log, so our base is 10, but it's not written because, again, it's a common log. When you look at this graph, note that the points 0, 1, that's 1 point, and then the second point 1, 10 are on the graph of y equals 10 to the power x. So these 2 points 0, 1, which is a y-intercept, and so meaning it's where the graph crosses the y-axis, and the point 110 are on the graph of y equals 10 to the power of x, which is the exponential function, and at the reverse point, so if we take the x-coordinate and y-coordinate of the point 0, 1, and we reverse them, so we write 1 first and then 0 second, and then we do the same thing with the point 110, we reverse the x-coordinate and the y-coordinate, and we rewrite it as 10, 1. These 2 points are actually on the graph of the inverse of y equals 10 to the power of x, which is the graph of y equals log x. So remember, when you take an inverse of a function with specific coordinates, to rewrite the coordinates of the new graph of the inverse, you're swapping the positions of the x-coordinate and the y-coordinate. So the x-coordinate of the original function becomes the y-coordinate of the inverse, and the y-coordinate of the original function becomes the x-coordinate of the inverse. You're swapping the input and output with inverse functions. Recall that the graphs of inverse functions are reflections of each other across the line y equals x. So remember, when we graph those inverse functions on the same set of axes and we looked at them, they were pretty much reflections of each other across that line y equals x. So the line y equals x is a linear equation. It goes straight through the origin. It goes from left to right upwards. And if you look at inverse functions, they're pretty much reflected across this line. That's how you know that two functions are inverse functions, just by looking at their graphs, if they're reflected across the line y equals x. You can graph y equals log base b of x as the inverse of the exponential function y equals b to the power of x. And this applies to any log and exponential function that are inverses of each other. So those are just like formulas to look at. And then here's a graph showing you those two functions. You have the exponential function y equals 10 to the power of x. You also have the point 1, 10 up here, and then you have the point 0, 1 down here. If we swap the positions of the x-coordinate and y-coordinate, you're going to get the point 1, 0, and you're also going to get the point 10, 1. And that actually belongs to the logarithmic function, which is the inverse of y equals 10 to the power of x, which is the exponential function. So that was what we were talking about on this slide. Now we're going to just do a quick problem number 4. It's all about graphing a logarithmic function. The instructions say, what is the graph of y equals log base 3 of x? Describe the domain and range, and then identify the axis, intercepts, and the asymptote. So we're graphing this log. We're also going to talk about what the domain and range is by identifying them in interval notation. Then we're going to identify where it intercepts the axis, and then where the asymptote is. So we're going to do all of that in this problem. Here's the solution already pre-written if you just want to just copy it down, and then we'll go over the problem together. And then here's the actual graph that you should be getting. It's a pretty straightforward graph, but since this is our first log function graphing problem, we'll work through it together. So what I'm going to do first is I'm going to rewrite the log function that we've been given, y equals log base 3 of x. And our first step is to rewrite this as an exponential function. That way, it just makes it easier for us to plug in values and then make an xy table so that we can actually graph coordinates on the coordinate plane. If you rewrite this as an exponential function, you're pretty much going to get x equals 3 to the power of y. So this is just like a regular exponential function, except we swap the positions of the x and y coordinate. We would get y equals 3 to the power of x for a normal exponential function, but since this is a log function written in exponential form, you end up getting x equals 3 to the power of y. And how did I get that? Well, it's pretty much that little e thing that I showed you all. So if I rewrite this, log base 3 of x equals y. That's an easier way to see it. If I drew that e, you'll see that 3 is going to be our base, raised to the exponent y is equal to x, and that's how you rewrite it in exponential form. That's how you convert from log to exponential form. So using this formula, we're going to make an xy table, and we're going to include 5 points on it. So what do we do here? Usually we'll pick our x coordinates and input them in, and then we'll get the y coordinates. But in this case, since we're raising our base to the power of y, we're going to actually pick y coordinates, and then we're going to get x coordinates as our output. Because remember, a log function is the inverse or opposite of an exponential function. So instead of inputting x as we would for an exponential function, this time we're going to input y. So if we can just pick really basic numbers centered around 0, which is the origin. So we can pick, we're picking 5 points, we can pick -2, -1, 0, 1, and 2, and then we can plug them in to our log function to figure out what x would be. So if we plugged in -2, 3 to the power of -2, well, we're raising to a negative exponent, so we're going to get into fraction. 3 to the power of 2 is 9, so we're going to get 9 in the denominator, and our x coordinate is going to be 1/9. If we input -1, 3 to the power of -1. Well, to the power of 1, we're just going to get 3, but we're going to get a fraction because we have a negative exponent. So 3 is going to be in the denominator, and we're going to have the fraction 1/3. If we input 0, 3 to the power of 0, any number to the power of 0 is 1. So that's going to be equal to 1. 3 to the power of 1 is just 3, and then 3 to the power of 2 or 3 squared is 9. So pretty straightforward. Using this information, let's next determine the domain and range. So the domain. The domain is going to be 0 to infinity. And how do I say this? Well, if you look at our y coordinates, which is what we're inputting, as you see, as we get smaller and smaller, so we're going to the negatives, we get a fraction. So we're getting smaller and smaller x coordinates. If I input, for example, -3, 3 to the power of -3, well, 3 to the third power is 27, a negative exponent, fraction, so 1 over 27. You can see that the fraction gets smaller and smaller, and it approaches 0. But if you keep decreasing your y value that you're plugging in, you're going to get smaller and smaller fractions, but you're never going to get equal to 0 because there's an asymptote at 0. There's a vertical asymptote at 0. That's why we just cannot get past 0. So the domain is going to extend from 0, not including 0. That's why we have a parenthesis all the way to positive infinity. So now let's talk about the range. Well, as you can see, the range can go all the way into negative infinity, go all the way to positive infinity. We can plug in any value we want for y. Usually, with functions, you can plug in any x value, and then you'll get a y coordinate out. Functions have continuous domains, but in this case, the function is the exponential function. The log is the inverse. So in this case, instead of the domain being continuous, the range is going to be continuous. So our range is going to be negative infinity to positive infinity. We also have to determine what the y-intercept is going to be, and we have to determine what the x-intercept is going to be. Remember, an intercept is where the function touches and crosses the axis. So we're looking at both of the axes in this case. So for the y-intercept, hopefully you can tell even without looking at the graph that there actually is no y-intercept, and I'll explain why. X equals 0 is the vertical line where the asymptote is. That's why we said the domain extends from 0 to infinity, because we're never going to touch 0. Because of that, y equals 0. X equals 0 because there's a vertical line there. And because there's a vertical line, what happens is we can't go to the left of that vertical line, meaning we are going to get closer and closer to 0. We're never going to touch 0. If we're never going to touch 0, we're never going to cross the vertical line x equals 0. And x equals 0 is a vertical line. It's the y-axis, actually. X equals 0 is the y-axis, just as y equals 0 is the x-axis. Meaning, if we're never going to touch x equals 0, we're never going to touch the y-axis. So we're not going to ever touch it or cross it, so we're not going to have an intercept there. However, for the x-intercept, we are crossing the x-axis. As you can actually see down here in our coordinate table, we have the point 1, 0. This is where our graph is going to cross the x-axis, so our x-intercept is 1, 0. Then lastly, we have to determine where the asymptote is. As we said before, the asymptote is the y-axis, my bad, and the y-axis can be written as x equals 0. Alright, so now let's actually graph this. I have a fresh graph, and let me erase what I wrote here. So in this graph, we'll pretty much just be putting these points that we found here, and then we'll be drawing an asymptote, and it'll just give us a better visual because on assessments, you'll most likely have to graph. And graphs, this is a very basic graph because it has no translations in it. It's pretty much the parent graph where base b has been changed to 3. But in normal situations, especially if you're in an advanced algebra 2 class, you'll be asked to graph log functions with translations, but don't worry, we'll get to that eventually. So let's simply graph this graph. As we said before, we have our vertical asymptote at x equals 0, which is the y-axis, so that's where I'm going to put this hashed line, just so I know that even when I sketch my graph, I cannot cross this line or my graph is incorrect. Our first point that we found was the point 1/9, -2. So 1/9 would be over here if I approximate it, and then -2 is down here. Our second point is 1/3, -1, which is about here. Our next point, which is the x-intercept, is 1, 0, so right 1 up or down 0. Our next point is 3, 1, so come right 3 up 1, and then our final point is equal to 9, 2, so come right 9 and up 2. Then if you just simply connect the dots, you'll see that this is a logarithmic function. It's essentially a exponential function on its side, if you want to think of it that way, because if we wrote the exponential inverse of this, it'd be a reflection across the line y equals x, which is this line right here. Hopefully you recognize it from our inverses unit. But that's pretty much it. That's the graph of this logarithmic function. So let's move on to the parent log function, and then translations. The parent log function is pretty much denoted by y equals log base b of x, is a parent for a function family, in this case the logarithmic function family. You can graph y equals log base b of, in parentheses, x minus h plus k. This is the translation, so by translating the graph, by adding the h and k into the formula, you're translating the graph of that parent function we're talking about, which is y equals log base b of x. The h actually horizontally translates it, so it'll translate it across the x-axis from right to left, and then by h units, depending on whatever h is, and then k will move it up or down. If k is positive, up; if k is negative, down. So you'll be moving vertically up and down the y-axis by whatever k units, whatever k is in the formula. And the a, in this case, I didn't write it, but you'll sometimes see an a thrown in front of the log. So the a in y equals a log b of x, so that's your same parent function, except we threw an a in front of the log. It indicates a stretch or a compression and possibly a reflection. So you'll have either a stretch or a compression depending on if a is greater than 1. Well, if a is greater than 1 or less than -1, you'll have either stretch or compression, and then it'll also depend if a is between 0 and 1, and then if a is actually also a negative number, you'll have a reflection. It's pretty much the same concept we were looking at with parabolas, depending on whatever a was in like standard form. So that's very similar to the log functions, and it'll go more into depth in the next slide after I show you this image. So as you can see, x equals -2 is our vertical asymptote that we're working with. The parent function in this case is y equals log of x. If we translate it horizontally by h, we translate it and we get a new function, y equals log of x plus 2. Well, whatever happens in that little set of parentheses will move your function left or right. If it's positive, it'll actually be moved left, and if it's negative, it'll be moved right, because it's minus h, so the signs will change. So in this case, because y equals log times log of x plus 2, you move right 2 units. So you can see that this function has been translated left 2 units. Then we have another function, y equals log of y equals 5 log of x plus 2. We have that same log of x plus 2, but we are actually changing the factor by 5 because we added the 5 in front of it. So these are all different types of translations you can have but everything is based off of that parent function that we've been working with. Next slide, we'll talk a bit more about the concept summary. So we'll be talking about families of log functions. Whenever we talk about a parent function, we're always talking about function families. In this case, we'll be looking at the log function family. The parent function, as we said, is y equals log base b of x. Our base has to be greater than 0, cannot be a negative number, and b cannot be equal to 1 because 1 raised to any exponent is just going to be equal to 1. So those are the criteria. When we have a stretch, so we're going to talk more about the a in this case, the stretch or compression factor. In order to have a stretch, which is where it's pretty much the graph is made like skinnier, you can almost think of it like that. A stretch is where the absolute value of a, so it doesn't matter if a is positive or negative, we're not worried about that right now. As long as a is greater than 1, or in this case less than negative 1, we have a compression or we have a stretch. However, in order to have a compression or a shrink, so the graph is made like wider, you can think of it like flattened. Compression or a shrink is where the absolute value of a, so a can be a positive or negative, but it's going to be a fraction because it's between 0 or 1. If a is a fraction, you have a compression or a shrunken graph. And then in order to have a reflection, a has to be less than 0 or negative, because if you have a negative number, if you have a negative a, it flips it and it'll reflect it across the x-axis. So it's pretty much going to be denoted as y equals a some number log base b of x. Let's talk about translations. You have horizontal translations by h, which is in the set of parentheses with x, and then vertical translations up and down the y-axis with the plus k outside. And you would denote that in the formula y equals a log base b of x minus h plus k, which you looked at on the last slide. And then if you put all of these transformations together, we'll just disregard the a for right now. You get y equals log base b of x minus h plus k, and then depending on if a is not equal to 1, if you have some stretch or compression factor, and if there's a reflection, you'll have a in front of the log. So that's all I have for you today. I hope you enjoyed the video, and please stick with it for more log function videos. I hope these videos are helpful for you all. If you did find it helpful, please hit the like button, the subscribe button, and the post notification bell. Drop a comment down below, and please share using our socials. You can also check out our website and Gmail for any of your inquiries. Thank you, and have a nice day. See you in the next video.